It's our pleasure to introduce on behalf of the FMRI Research Institute and the WTS and IT student chapter, the Dr. Alluri, Associate Professor from the International University, to be part of the FMRI webinar series. I will ask Anika, the WTS president for FAU, the IT president, for FAU to introduce Dr. Alluri. Thank you.
Hello, everyone. Good afternoon. I'm Anika Tabassum. I'm the president of FUIT student chapter, and so I'll be the moderator of today's event, along with our vice president, Alluri Machado. If you have any questions regarding the presentation, you can type it in the chat box or speak up at the end of the presentation. Alluri would be taking all your questions at the end. Today we have with us Dr. Priyanka Lowry from Florida International University. Dr. Alluri is an associate professor in the Department of Civil and Environmental Engineering at the Florida International University. Her research has primarily focused on secondary crashes, freeway incident management, transportation systems management and operations, connected vehicle technologies, safety of vulnerable road users, wrong way driving mitigation, and application of the advanced safety analysis tool. Dr. Alluri currently serves as the Vice Chair of the IT Transportation Safety Council and also the Faculty Advisor of FIU IT Student Chapter. Thank you for your time, Dr. Alluri, and we are excited to hear your presentation now. Now the floor is yours.
Okay, thank you so much. So good afternoon, everybody. I'm Priyanka Lowry, a faculty at Florida International University. Before I start my presentation, I would like to thank FAU FMRI for inviting me to give this presentation. I was so excited. I was hoping to actually be in person and give this talk in person at FAU, but hopefully sometime soon. But this is the best that we could do. So here we are. So in this presentation, I'm going to talk about the role of TSM&O, which is Transportation Systems Management and Operations, in improving freeway operations. So I have 47 slides, so I will try to finish that up in 40 slides, but sometimes I get carried away and I can speak for 3 hours. So I have a note to self and a timer to make sure that I don't take too much time, but we will see how it goes. So in this presentation, I'm going to talk about basically 5 things. The first one is just to introduce to everybody what is TSM&O and why do we need TSM&O. And then I'm going to go in depth about and discuss about 3 strategies, which are RAM meters, dynamic message signs, and express lanes. Just as a disclaimer before I start the presentation, it's my students who do all the work and I'm just here to talk. So if you have any questions, I will try to answer to the best of my abilities, or else I need to text them or call them to provide specific answers. But anyways, so I want to give credit to the students who have been working on this project on these topics. RAM meters, it is Henrik, whose dissertation is on this topic on RAM meters. And Cecilia is my other student who helped me with dynamic message signs and express lanes. And her dissertation is on express lanes. So yes, so it is all the students' work, and I'm here just to present their work on their behalf. So coming back to our topic, so the question sometimes students ask me, and most of the transportation professionals are aware, but they ask me is, what is TSM&O? So the way I see it is, when we talk about the safety and mobility, when we want to have a transportation network that is congestion-free and fatality or serious injury-free, we have 3 divisions within the Department of Transportation, or for that matter, any agency that works towards achieving these goals. Those are the traffic operations. There we have the traffic engineering principles and practices that are put in place and deployed and implemented. And we have the ITS, which is Intelligent Transportation Systems. And these are technologies that could be adopted in order to, again, improve the safety and mobility of the transportation network. And now we have this third bubble, or the division, I call it, is the TSM&O, which includes the processes, procedures, policies, and agreements to use the technology, the ITS technology, and the traffic engineering principles and practices. So the way I see it is that when all of these 3 divisions, the traffic ops, ITS, and TSM&O work together, that is how the safety and mobility goals of the agency could be achieved. I know it's a little confusing to explain what TSM strategies are. So I do have a couple of examples. Say, for example, we are all familiar with sitting in traffic, say, for example, on I-95. And what do you think is a solution for this one? Maybe let's add more lanes, or maybe not. So adding more lanes is considered as a conventional improvement, as a traditional improvement in order to improve mobility on a freeway, for example, on I-95 in this example. Or we could look at TSM strategies where we can invest in express lanes, also called as managed lanes, where we may or may not expand the footprint of the roadway, but still add express lanes within the existing right-of-way in order to improve the mobility so that we have less congestion, and also the congestion is for a less amount of time. I will, as I said, I will discuss in detail about the performance of these express lanes later, but this is one of those TSM strategies as an example, which is very different from the conventional improvement of, say, adding more lanes. Let's consider another example. So we have a freeway. In this case, this is just an example. So we have 4-lane freeway and a ramp and an on-ramp. And as you can see, you have a lot of traffic coming from the ramps onto the freeway. And again, what is the solution? What is the traditional solution? One of the traditional options would be, let's add more lanes, both on the freeways and or on the ramps, so that we can move more traffic. But again, a more cost-effective and efficient and quickly implementable solution could be to use RAM meters. What are RAM meters? They are just traffic signals at some of the on ramps. Yes, we do have signals on ramps and in the vicinity of freeways, but these signals will meter the entering traffic so that traffic is not only a certain number of cars enter the freeway main line in a certain amount of time. So in that way, the performance of the freeway's main line is improved. So again, this is another TSM strategy that improves the operational, and as you will see later in the presentation, also the safety performance of the freeways. And yes, and I do have one more example, and I don't have a before and after or in conventional versus TSM strategy pictures here. But in this example, what I want to say is how dynamic message signs, the signs that we see on freeways quite a lot, they provide the travelers the information that we as travelers or drivers need in order to make informed decisions. Say, for example, if you have a crash downstream, and if you have the DMS that says crash ahead, use caution, or crash ahead, detour, and drivers, people like me who actually pay attention to the signs, may actually detour, reducing the traffic upstream of that incident or crash, and also reducing the probability of secondary crashes. So the dynamic message signs, as I said, could be another relatively low-cost TSM strategy that could improve the operations of the freeway. So what I said so far, these are just 3 of the many examples of TSM strategies that could improve both safety and mobility of the freeway operations. So as I said, now that we know or kind of have an idea about what potential TSM strategies are, let's go in depth about what these could do. First thing is that these TSM strategies are integrated, and it's not like they work in isolation. So they work together. Say, for example, as you can see in this figure, you can definitely see the express lanes and the dynamic message signs, and you can also see, maybe you can't see them, but you do have CCTV cameras, and also, as I said earlier, RAM meters. So all of these, arguably 4 TSM strategies, are working on the same corridor in order to improve the safety and the operational performance of this freeway corridor. And hence, with this slide, what I want to say is that the TSM strategies are integrated, and it's not just one strategy that works. I mean, that could be the case, but in general, we would be having multiple strategies to help alleviate congestion and improve safety on a facility. And another important factor that separates TSM strategies from the rest of the conventional strategies or conventional improvements or countermeasures, if you will, are that the TSM strategies are performance-based. So it is and outcome-oriented. By that, what I mean is all the TSM strategies are geared towards improving safety and or mobility. And I don't want to say either safety or mobility, because the way I see it is that safety and mobility are so intertwined and interlinked that you can't improve one without improving the other. Or in other words, if you improve mobility, safety will almost always necessarily be improved. Again, there is a caveat in most cases. And at the same time, if you improve safety, mobility also to an extent, in majority of the cases, will be improved. And some of the mobility performance measures are travel time reliability, which we'll talk quite a bit in this presentation. Also, the incident response time, incident clearance time means how quickly an incident has been responded to and how quickly is that incident cleared, and also travel delays. And with respect to safety, what we have are usually two major performance measures, which are crashes, which is always the case. We always want to have our vision zero, which is zero fatalities and serious injuries. And we also have secondary crashes, which are crashes that are because of the congestion that is caused because of a prior incident. I don't want to go into details about what secondary crashes are, but those two are commonly used performance measures to evaluate the performance of TSM&O strategies. Sometimes we also use surrogate safety measures, like, say, reduction in travel speeds, reduction in the variance of travel speeds, and coefficient of variation, in order to quantify the safety benefits. So, and also TSM&O strategies are at all stages. They are the planning, the project development, and also at the operations and maintenance. So TSM&O strategies, at least the way I see it as recently been, is that they are not an afterthought. TSM&O strategies have become a part or component of the planning phase, where potential strategies or alternatives in order to alleviate congestion or improve safety are considered. And they are also a part of the project development process and obviously the operations and maintenance. And just want to say that I am not biased towards freeways. It's just that a lot of my research projects have focused on freeways, but I also want to mention that TSM&O strategies are multimodal, and they are not just dedicated to freeways. It's easier to analyze TSM&O strategies on freeways. But having said that, we do have several TSM&O strategies that are focused on pedestrians, bicyclists, park and ride facilities, transit facilities. For example, transit signal priority is a good example, or emergency vehicle preemption, or we have adaptive signal control technologies, and so on and so forth. So TSM&O strategies are multimodal. It's just that in this presentation, I chose, just because I can't, I don't want to keep you for like 4 hours today. So I just wanted to focus my presentation on freeway operations. So in summary, what I want to mention is that these TSM&O strategies focus on 3 things. First one is to preserve the capacity of the facility, to improve safety and security, and to improve the reliability of the transportation network. So to make sure that the transportation network is much more reliable, safer, and mobile events basically have less congestion. So coming back to TSM&O in the context of Florida, for example, in 2017, it's been quite a while actually. 2017 is about 3-4 years ago. So FDOT's 2017 TSM&O strategic plan gives like it's almost like it's not called a strategic plan, but it's almost like an action plan to see how TSM&O strategies could be deployed and implemented and considered as part of the alternatives in the analysis. So the vision of the plan and of the DOT is to have a fatality-free and a congestion-free, and that itself tells that safety and mobility are the most important factors that the Department of Transportation, FDOT, is considering with respect to their transportation network. And the mission of this strategic plan is to identify, prioritize, develop, implement, operate, maintain, and update TSM&O strategies. And I want you to pay much more attention to the next phrase, which is measure their effectiveness for improved safety and mobility. So one of the major takeaways for me from reading the strategic plan was that the TSM&O strategies are there, but very rarely have they been quantified in terms of how effective they are. Anecdotal evidence, yes, great. We know that express lanes improve safety anecdotally, and we know that from just talking to the general public or getting the public opinion, we know that the dynamic message signs provide valuable information to the public. But we have not yet, up until this project that we got a couple of years ago, that we were able to quantify the effect of these TSM&O strategies. How effective are RAM meters in improving safety, in reducing crashes, or in increasing travel time reliability, or in increasing the average travel time? So those are the questions that we attempted to answer in the research project that we recently completed. It's recent, but it was actually a year ago, that focused on the performance of the TSM&O strategies. Okay. So from the remaining slides, I'm going to focus more on those three strategies. As I said, the RAM meters, the dynamic message signs, and the express lanes. So again, the RAM meters, these are the traffic signals along the freeway on-ramps to control and regulate the frequency at which the vehicles join the freeway main line. So advantages, as I said, is to manage the demand on the freeway main line and also help break up the platoons by controlling the rate at which the vehicles enter the freeway main line. Deployment, so far in Florida, we have the RAM meters operational on I-95 in Miami-Dade County. We have about, okay, I forgot the number. I think it's 10 on one side, 12 on one side. So I think it's 22 RAM meters on northbound and southbound combined. And coming soon, hopefully this year or next year, I'm not sure, because the website said they're due to open in 2020, but COVID threw us a curveball, so I don't know. But coming soon, we do have another deployment of RAM meters on I-95 in Broward County. But in our analysis, which, as I said, Hendrik was the one who did this analysis, and it's his dissertation. So if you have any questions, knock on his door. I'm kidding. I can answer the questions, but yeah, it's his work. So he focused on the I-95 in Miami-Dade County. So the data we used is the traffic data from RETAS, and we used 3 years of data, so 2016 to 2018, and we received the RAM metering signals, RMS, operations data from District 6, RTMC. By operations data, what we received were like when were the RAM meters turned on, when they were turned off, and the reason. And we collected the roadway characteristics and contextual data, which is just the RAM, where the on-ramps are, from Google Maps, and we got the crash data from Sunguide. And again, for each of these strategies, I kind of like divided them into safety benefits and mobility benefits. So here, for RAM meters, when we're talking about the safety benefits, what we did was that we identified the crashes that occurred when the RAM meters were turned on, and we identified similar scenarios where there was no crash, and we compared the performance of those two. So we have a few crash scenarios, and then we identified similar non-crash cases, and then we use all of that data to model. And since we have a lot of very few crashes and a lot of non-crashes, so we had to do bootstrap resampling in order to increase the sample size. And we analyzed based on crash precursors, which are the traffic flow characteristics prior to the crash, to see what factors contributed or resulted in that crash. So these are the results. On average, this is based on the FDOT report. I forgot the report number, but I think you can just Google RAM meters and FIU. I'm sure you will get this report. But what we found was, in terms of safety benefits, we found that the RAM metering decreased the crash risk by 41%. And on the left, when you can see that the crash precursors, these are, say, when the crash precursor is the RAM meters are turned off. That means you have a congested time and the RAM meters are turned off because there was a malfunction. And during that time, the average downstream volume, the traffic volume on the freeway main line, downstream of the RAM, was a good indicator of whether we would be whether that segment would be experiencing a crash or not. And when the RAM meters are turned on, it's usually speed, occupancy, and volume. The average of those, and also the coefficient of variation, which just tells how the speed, occupancy, and volume are varying. So these are some of the factors that we identified to be to contribute to the occurrence of a crash. And agencies could use this information in order to effectively and efficiently deploy responding agencies, and also turn on or basically activate RAM meters. And based on the mobility benefits, what we did was we compared the RAM meters when they're turned on versus when they're turned off. Again, this entire analysis is just focused on recurring congestion. So we're not focusing on the non-recurring congestion. In fact, Henrik is doing that right now, I believe, as part of his dissertation as an extension. But this presentation or this research is just focusing on the recurring congestion. And what we found was that for mobility benefits, what we used was the buffer index, which is a travel time reliability. And what is buffer index? It is a time cushion, the amount of additional time that most travelers would add to their average trip in order to make sure that we arrive on time. And what we found was that when the RAM meters are turned on, and when a driver uses the facility during moderate congestion, then the buffer index is reduced by 22%. And during severe congestion, say morning peak hour or evening peak hour, the RAM meters would reduce the buffer index by 30%. Let me put that in perspective. Say, for example, I'm an FIU, and if I have to if I'm planning to give this presentation in person at FAU, the travel time is about 60 minutes. So if I have to be there on time, that means at 1 o'clock, I would put a buffer of, say, 15 minutes or 20 minutes, let's say, so that I would start here at 11:40 to make sure that I am there at 1 o'clock. But if you have RAM meters turned on, assuming that during afternoon time is moderate congestion, if the RAM meters are turned on, I don't need to put a 20-minute buffer. I could go with a 15-minute buffer. So instead of going starting at 11:40 in order to make sure that I'm there at 1 o'clock, I could start at 11:45. So that is how much RAM meters could affect, and that is how we quantify the mobility benefit of activating RAM meters along the corridor. Of course, I don't think that example makes sense because I don't think I will be taking I-95 to go to FAU, or maybe I do. I don't know. I follow Google Maps, so I don't know. But you get the point. So that is how the mobility benefits of RAM meters was quantified. Now, switching gears a little bit and moving to dynamic message signs. What are these? These are signs, and we see everywhere, especially on freeways, where these signs are used to disseminate real-time information. Sometimes it's used to disseminate information such as travel time, or maybe crash ahead, or any incident downstream, or weather, adverse weather, or sometimes it's alerts like click it or ticket, don't drink and drive, put your cell phone down, information like that. So what we wanted to do is, like, this was actually one of the difficult strategies to evaluate, because it's quite interesting to see how can you quantify, like with the data, how effective displaying a message on a dynamic message sign is. So that is what we were trying to tackle with this strategy, and Cecilia was the one who was working on this strategy. So if you have any questions, ask her. I think I can answer, but she's the person to go. So in general, overall in Florida, we have about 900 or 869 DMS signs, and they're operational 24/7, and they convey time-sensitive information. Mostly it's travel time or incident information, or advisory information such as click it or ticket, don't drink and drive, don't text and drive, etc. So some of the advantages of dynamic message signs are that they reduce secondary crashes, they minimize travel delay, they provide motorists with the information they need to detour, reroute, or to plan accordingly, or to change their travel behavior accordingly. By that, with the next slides, I think you will have a better idea as to what we're trying to say. So again, we wanted to evaluate the safety and mobility benefits of displaying a certain type of a message. And in this case, we focused on crash-related message on a DMS sign. And our study corridor was I-95, and we used 3 years of data, 16 through 18, and we focused on locations with 23 dynamic message signs. So we needed 3 types of data, just as with RAM meters. So we needed from the district TMCs, we needed the dynamic message sign locations and the dynamic message sign logs. What information was displayed at these signs and for how long? Say from 1255 to 107. Then the information that was displayed was crash ahead, use caution. Information, data like that. And we also needed data from RITIS, which provides the real-time traffic data, which would be speed, volume, and occupancy. That's almost like the same. We've used that for all of our strategies. And we obtained crash data from Sigma 4, which includes time, location, and other factors such as crash severity. So how did we quantify the benefits? So this is just a schematic of where the dynamic message signs are, for example, and what we called as an upstream detector, which would be up to 1,000 feet upstream of the crash of the DMS. Why we chose 1,000 feet? Because we found out that that is the distance that a driver could see, from which a driver could see the DMS sign. I don't think I asked Cecilia to drive through these 23 locations to see when she can see the signs, but from research, we found that 1,000 feet is an acceptable distance to consider. So the upstream would be the upstream detector, and the detector downstream of the DMS is what we consider to be the downstream detector, from which we collected the data. I know this slide is a little busy, but I just wanted to make it busy so that you pay more attention. But in general, what I'm trying to say in this slide is that for the dynamic message signs, what we did was we identified the times when the DMS displays a crash-related message. As you can see in the example here, that would be crash 3 miles ahead, use caution, for example. And we compared the performance of the drivers in terms of average speed, coefficient of variation of the speed, and actually occupancy doesn't make sense, but average speed and variation of speed with the clear messages. Clear message is a message that is not related to a crash, but which does not require drivers to react to. Say, for example, buckle up, click it or ticket, no reported delays, no incidents, messages like that. So what we did was we compared the travel speeds when drivers see or saw a crash-related message and see if they are actually changing lanes, and compare those with the driver's speed and when they're changing lanes, when the message on the DMS was a clear message, which is nothing related to a crash. So this is what we found. And so when the DMS displays the crash-related message, which may be crash ahead, use caution, or crash ahead, left lane blocked, this is what we found. We found that drivers slow down. The average speed upstream of the DMS sign, the drivers slowed down looking at the crash message. We found that, interestingly, that the speed variance increased. That means drivers were reacting to that sign, whether they are changing lanes or maybe aggressive drivers sometimes speed up because they know that there is a crash, downstream, and they want to go as quickly as possible, maybe. And hence, conservative drivers may slow down, and maybe that is the reason why we saw speed variance shot up. And what we saw was we did not find any significant increase or actually any significant number of crashes downstream of the DMS. So this is contradicting in a way, because how can you have, because we usually say that when you have a lot of speed variance, that is a surrogate measure for crashes, right? You have a lot of higher speed variance means you will most likely have crashes. But that is not the case. And the way I see it, or I think it in my head, is that people are cautious. They know that there is a crash ahead. So there is a lot of speed variance, but people are not distracted. They're cautious. And that's why even though we observed an increase in the speed variance, there were no adverse safety impacts, if that makes sense. So these are the benefits of dynamic message signs. I kind of like combined mobility and safety benefits in this way. And the study limitations are that the reduction in speed, we are unable to attribute it to only the DMS signs. It could be because people are using Waze or they're listening to highway advisory radio, which also disseminate the same information. So we are unable to separate those two, and that is one of the major limitations of this study. And also, we did not consider other factors that could have resulted in the reduction in the speed. For example, there may be other incidents on the downstream that may have resulted in higher speed variance or lower speeds, but we are unable to consider those. Okay, so I have 7 minutes or so, I think, we will see. So now coming down to the last strategy, which is the express lanes. As we all know, express lanes are managed toll lanes. These are the way I call them as like the freeway within a freeway. We separated from the general purpose lanes that have a higher level of service or a better level of service. So they are deployed everywhere, mostly, but they are in operation. We have about 62 miles, but we have about 100 miles under construction and about 300 miles in either planning or the design phase. Advantages: they reduce overall traffic congestion, they improve safety, and they increase the overall capacity of the highway. So when we are tasked with the task of quantifying the mobility benefits, we did two things. We compared the performance of express lanes with that of the general purpose lanes. Just again, express lanes are the lanes where we pay a toll to go on them, and the general purpose lanes we don't pay at all. And then we also compared the performance of the general purpose lanes when the express lanes are open versus when they're closed. So these are the two types of comparisons that we did. And I believe we published this paper in TRR. Yeah, but this is Cecilia's work. So the data, again, radius data, express lanes operations data, and contextual data from Google Maps. I'm going to skip this because we don't have time. So it's very difficult for us to visualize what we're trying to do. So this is what we're trying to do. First thing is we're comparing the performance of the general purpose lanes when both are open, and the one in the right car and the white car. But when they're open, that means people can move into the general purpose lanes, from general purpose lanes to express lanes. And we compared the performance of the general purpose lanes in this scenario with when the express lanes are closed. So people have no choice, or drivers have no choice, but to just continue on the general purpose lane. And when we compare these two scenarios, this is what we found. And our comparison is based on buffer index. And again, the lower the buffer index, the better it is. Means the more reliable the travel time is. So the lower, the better. I mean, the left is the one for northbound, and the right is the one for southbound. I mean, they show similar trends. So we can just focus on one. Say, for example, the northbound. So the red lines are the buffer index of general purpose lanes when the express lanes are closed. So people have no choice but to travel on the general purpose lanes. And in that case, as you can see, the buffer index, the red line is higher. And it is higher and it is much more irregular compared to the blue line, which is the buffer index on general purpose lanes when the express lanes are open. So the blue line is much more smoother and is lower than the red line, while the red line is very inconsistent and is also higher. So what does it tell? It tells that when the express lanes are open, general purpose lanes perform better. And this is another scenario. This is when both express lanes and general purpose lanes are open. In this scenario, what we're trying to see is on this facility right now, whatever you're looking at, when the express lanes and general purpose lanes are open, we wanted to see how they're performing, the express lanes and the general purpose lanes. And this is what we found. And so this is what I'm calling them as express lane facilities, because we are comparing the performance of general purpose lanes and the express lanes. And the blue is the performance of buffer index of general purpose lanes, and the red is the buffer index of express lanes. The left is northbound, right is southbound. They are similar. We can just focus on one. As you can see, Red line is lower than the blue line. That means express lanes are better or more reliable than the general purpose lanes, except for the morning peak for the northbound, and actually it's for both morning peak and the evening peaks. For some reason, the morning peak and evening peak, just during that peak time of just the 30 minutes or 1 hour, our buffer index for express lanes is higher than the general purpose lanes. But overall, in general, the buffer index for express lanes is much lower than the buffer index of the general purpose lanes. And all of these results are statistically significant. I mean, we did the test, and all of these differences are significant. So the results, in short, that when express lanes were operational, the performance of the general purpose lanes improved. So no matter, and in general, when both the express lanes and the general purpose lanes perform better when the express lanes are operational. So in general, tying it back to the first example where I did the conventional improvement versus TSM&O strategy. And so if we have this same roadway footprint, based on our mobility analysis, what we found is that if you have express lanes and reduce the number of general purpose lanes, the performance of both the general purpose lanes and the express lanes improve. So that is the mobility component, and this is a safety analysis. And this is a recently we just got this project. Actually, it feels like a few months ago, but yeah, we're in the process of completing or working on this research project, which focus primarily on the safety analysis of express lanes. And the goal is to quantify the effects of separation types, the managed lanes or express lane separation types, on the safety performance of these express lanes facilities. And for this research project, this is ongoing. We have 3 objectives. The first one is to develop the safety performance functions under specified base conditions. The second objective is to develop the crash modification factors. And our focus is to develop these CMFs for different separation types and other geometric attributes. And the third objective is to develop the severity distribution functions to estimate the expected frequency for different severity levels. So since this project is ongoing, I don't have any results as of today, but once this is complete, this is what we will produce. The project requirements are the SPFs, CMFs, and SDFs. This is a typical safety research project, I would say. And in addition to the project requirements, we are also producing other byproducts, which would be a spreadsheet application, so that it's easier for practitioners to implement do the analysis, and a GIS inventory of managed lanes, 1-page summaries of the results, and a 1-hour recorded webinar, and a set of sample problems for professionals and practitioners to use. So in this project, what we are focusing primarily are on the separation type, as I said, and we have 3 separation types. We have the pavement marking buffer separation, where the separation between the express lanes and the general purpose lanes is just a buffer and just dotted lines or pavement markings. And we have the concrete barrier that separates the express lanes from the general purpose lanes. And we also have the pylons, which are on I-95, where we have these pylons that separate the express lanes from the general purpose lanes. We also have the wide median buffer separation. However, we are not focusing on analyzing that, so we'll be analyzing on everything else except the wide median buffer separation. As I said, the project, I don't want to use the word just started, because the kickoff meeting was in June, and we are halfway through it, and we are in the process of data collection, analysis, and development. So we will have the results and everything ready by the end of this year, November. So that is the project that's going on. So this is my last slide. So in summary, just bringing it all together, what we found is that, having worked on TSM&O strategies quite a bit, what we found is that TSM&O strategies are proven to improve the safety and the mobility, overall the operational performance of the transportation network, not only freeways, but also for arterials. But what we found is that the safety and the operational benefits are unique to the strategy. say the benefits for, say, for deploying gram meters, even the performance measures are different from the performance measures that we could use to evaluate managed lanes, which would be different from the performance measures that we use to evaluate, say, dynamic message signs. And also, not interestingly, it should not be surprising, but while some strategies provide direct quantifiable benefits like gram meters, managed lanes, if you come to arterials, we have transfer signal priority, we have adaptive signal control technology. It is difficult to measure the impacts of some strategies. For example, dynamic message signs. It was difficult to come up with a robust research approach to quantify the benefits of dynamic message signs using data. And also, how do you quantify the benefits of having CCTV cameras on freeways? So some strategies, it is a little bit difficult to quantify. And in general, overall, the TSM&O strategies provide feasible alternatives to achieve the safety and mobility goals of the agencies. So that is, I think, would be one of the takeaways from this presentation. But I think that is all I have. Oh, yeah. So again, I just talk. I don't do any. I don't work. Actually, I do work. But this is my research team, and I would like to thank each and every one of them for helping me put this presentation together and helping me with the research projects. I don't have the names there, but I think I remember them. We have Angela, we have Jimoko, Sultan, Cecilia, Henrik, John, Nafis, and my programmer Hyphen. So this is my research group as of today, but yeah, so they do all the work, I just talked. But yeah, so thank you everybody for listening to this presentation. And if you have any questions, comments, I hope I did not go over right on time.
Thank you so much, Dr. Alluri, for your great presentation. It was very interesting to learn about TSM&O and FDOT's initiatives. We will be taking questions now. So anyone type in the chat box, or you can mute where you feel more comfortable. Just remembering that this presentation, the slides will be available in the FMRI website. Its recording will be in the FMRI YouTube page and also on the website. So over the next few days. So does anyone would like to unmute themselves and talk or sending in the chat?
Meantime, oh, you have a question? Yes.
Did you receive a question?
No.
Okay. Yeah, usually people are shy to send questions.
I understand, but I forgot to mention, but I would like to thank FDOT Research Center and the Traffic Engineering and Operations Office for funding these research projects. And everything that I presented is a part of a research project that we completed last year. And the managed lanes, the safety benefits of managed lanes is an ongoing research project with the Traffic Engineering and Operations Office. So I would like to thank Research Center and the FDOT Center Office for funding this research project and for seeing value in these research ideas and implementing them and deploying these strategies and helping them quantify them as well. Okay, still no questions?
Okay, I think I got a question.
Okay.
Regarding the RAM meter. So you mentioned you're gonna place a kind of a signal at the ramp. Wouldn't be the bad side of it that you're building traffic on a local road, or kind of building traffic on the local road or the frontage road, whatever it's leading to?
Yes. Actually, thank you very much for that question, and you are correct. Sometimes when we limit the entry into the entry of traffic onto the main line, we inadvertently build up traffic, and that traffic may go all the way up into the arterials, and that would affect the performance of the signals within the arterial network. So that is correct. But in the bigger scheme of things, if we have to, if we want to focus more on pushing is not the word, or moving as much of traffic as possible on the freeways, RAM meters is one of the solutions. But that could be alleviated to an extent. That impact of RAM meters on the signals could be alleviated by retiming the signals and using other strategies at the signals to improve the traffic. But you are correct. You are totally correct that a more comprehensive approach would be to evaluate the performance of the entire transportation network in the vicinity of the RAM meters as a whole, and not just evaluating the performance of the freeways. Yes, that could be a research project for my other student, but yes, yeah, that would be a better.
Thank you. So the main purpose is to avoid crashes, or the main purpose of the TSM&O is to regulate traffic, or both of them?
I'm sorry, what was the question, sir? Sorry.
The question is the purpose of the role of the TSM&O is to avoid the crashes, or to have the traffic flowing smoothly?
That's a good question. The way I see it is like safety and mobility, they go hand in hand. They're together. Once you improve safety, once you avoid crashes, congestion is relieved. You will not have non-recurrent congestion and traffic flows smoothly. And when the traffic flows smoothly, when you have higher average travel speeds and less speed variations, then then you don't have as many crashes, because speed variance is one of the surrogate measures for safety for crashes. So they both go together. You can't improve one without improving the other. Or in other words, if you improve safety, mobility will be improved in most cases. And if you improve mobility, in most cases, safety will be improved.
Okay, I got it. Thank you.
Thank you.
Do we have any other questions? Anyone sending in the chat? Sometimes people send questions in the private mode, but it's not the case for me. Dr. Kaiser, would you like to conclude?
As always, Dr. Alluri, a very great presentation. We know that here in Florida, the Florida DOT has spent a lot of money on TSM&O, a lot of research going on, and I'm very glad that universities and faculty like you are involved with these projects, that they try to improve the congestion and the freeway operations in Southeast Florida. I don't have any question. I would like to ask the audience if they have any question on succession. If they don't, really appreciate Dr. Alluri your time, and we're looking forward to see you on campus in the near future, or in the next IT WTS events for FAU. Thank you.
Yes, thank you, Dr. Alluri, for presenting for us today. And just reminding everyone that our next webinar will be on March 30 with Dr. Leticia Dablan, which will talk about gig workers for delivery platforms. So if no one has any other questions, we can close this session soon. Thank you, Dr. Alluri.
Okay, thank you so much. And I would once again would like to thank FMRI for giving us this this opportunity to present. And I look forward to collaborating with ITE and WTS student chapters at FAU. And one silver lining from this COVID is that we are collaborating more with these webinars and other events. So I'm looking forward to more collaborations. And so thank you very much for for having me.